You may have terms like s minus a or s minus a square or s minus a cube and so on and so forth, right? So that means you have linear factors. Okay, I mean, this we can remember always. Linear factors of, say, any multiplicity, right? Say of multiplicity n, right? S minus a or s minus a square means we have a linear factor but of multiplicity 2, right? Similarly, s minus a cube means we have linear factors but of multiplicity 3, and so on and so forth. So that means if we have our expression in which we can say that this term rs can be decomposed as linear factors of multiplicity n, then to split it into partial fractions, we just follow this rule. A1 upon s minus a plus a2 upon s minus a square and so on and so forth plus an upon s minus a to the power n. यही होता है ना, where a1, a2, an are constants, right? So this we have been following, and this we know from our knowledge of partial fractions as well, right? Now similarly, if you have quadratic factors, right, say quadratic factors would mean you have terms like, you can split the terms like this, something like this. See, there is a difference. Either you may have terms like this or s square minus k square, or you may split it like this. अब इसमें difference हो गया ना. For this you have standard results, right? For this, what is happening is that you are actually undergoing a translation of x's, because हम s की जगह अब हम क्या use कर रहे हैं, s minus a, right? So if we have quadratic factors of this kind, so this actually will answer your question number 15 of 7.2 also. Maybe you can split it like this, right? So if you have something like this, then of course it may be just this term, or even this kind of a factor could be of any multiplicity, say n. So that means you may have terms like s minus a square plus b square, or s minus a square plus b square whole square. So that means you have a quadratic factor but of multiplicity 2, right? Similarly, you may have a quadratic factor of multiplicity n. Are you getting the point? So in case your term, I mean your rs, gets decomposed into this term and into terms of these kinds in your denominators, then your partial fraction, see, what do we do for one quadratic factor? We always say a1s plus b upon s minus a square plus b square, right? Similarly, if it's of multiplicity 2, then you will have a2s plus b2 upon s minus a square plus b square whole square, and so on and so forth. In case it's of multiplicity n, then we'll have a1s plus bn upon s minus a square plus b square to the power n. Now, is this clear? If you have linear factors or quadratic factors but of multiplicity n, right? Now in both these things, the objective is then to find the inverse Laplace of rs. Okay, so that means we first of all have to decompose this term. So that means the first thing that we need to do is the partial fraction decomposition of rs, right? And then we have to find the inverse Laplace of each factor of, say, each fraction that we have actually decomposed. This is the standard procedure that we have been following so far, right? But then if you observe one thing, whatever problems you have tried so far, your terms were just s or s square plus k square and things like that, right? So you could directly apply the results the standard results of inverse Laplace to each of the fractions that you decomposed, and you get the result, right? But now we don't have terms like s or something like this. We have terms like s minus a. We have terms like s minus a square, and so on and so forth. So how to find the results for terms like this? So in a way, what we have to see now is, can we just, derive results for the standard functions, Laplace transforms of the standard functions in terms of s that we already know? Can we derive those in terms of s minus a also? So that is the problem now. So that process of finding the, Laplace transforms in terms of s minus a, we are actually, the moment you have s minus a, so it's just that you are actually translating your x's. So that's why the theorem also, it just it just talks of the translation of the s axis. So instead of s, we'll be talking of s minus a. So the procedure is just the same. The way we translate our coordinate axes in Cartesian system of coordinates, when we have x and y, we talk of x minus a or x plus a, whatever we want to talk of. In a similar manner, we'll be talking of the translation, but for the s axis. Okay. So for that, we have a theorem, okay, which says that, if this is what your theorem on translation of the s-axis says, that if fs is your Laplace transform of ft, okay, so that means, of course, that means this small f satisfies all the conditions for the existence of the Laplace transform, okay. So, and this Laplace transform, we say this exists for s more than c, some c, okay. Then the theorem says that the Laplace transform of e to the power at ft also exists, okay, for s more than a plus c, okay. And in that case, the Laplace transform of e to the power at ft is actually equal to f of s minus a. Okay. Now, the moment you have this result, see, that means what? If that means what? That means we have some c here, so that for s more than c, the Laplace transform exists. The c can be 0 also. So for every s more than 0, the Laplace transform is going to exist. But then it says that we can always find some a here. This a exists such that this Laplace transform also exists. Not only this, the Laplace transform of e to the power at ft is actually f of s minus a. What was f of s? The Laplace transform of f of t. So what is happening? You are just replacing your s by s minus a in this capital F, and that happens to be the Laplace transform of e to the power at ft. So the moment you have this, that means the inverse Laplace of s minus a is actually e to the power at ft. So if you know small f, capital F, I mean the relations, that means we know that. See, for standard functions as small f, we know their capital F, right? So if we have to find the inverse Laplace of s minus a, it's going to be this term only. Is this clear? See, we can use it somewhere. See, for example, okay, let's see the first result that we have. What is the Laplace transform of t to the power n? What is it? What is the Laplace transform of t to the power n? अभी सबके आ जाएंगे, ये तो याद होने चाहिए. Laplace transform of cos kt, Laplace transform of sin kt. क्या होता है?
n factorial upon s to the power n plus 1.
N factorial upon s to the power n plus 1. And this happens for what s? S more than what?
S greater than 0.
S greater than 0. ठीक है ना? So that means in this case, if I see my C happens to be 0, right?
Yes.
So if I have this, that means if I use the result, the theorem that I just stated, that means the Laplace transform of e to the power ATTN, I don't have to evaluate it. I don't have to find the integral. I can directly substitute here. It's going to be s minus a to the power n plus 1. This is what the theorem says, that it is going to be capital F of s minus a rather than f of s. But then this has to be true for every s more than a plus c. But what is your c in this case? 0. So that means this is going to be true for every s more than a. Is it okay now? So that means while solving initial value problems, if you come across terms like 1 upon s minus a to the power something, then the inverse Laplace is going to be something like e to the power ATTN. Is this clear? Similarly, what is the Laplace of cos kt?
S upon s square plus k
S
square.
upon s square plus k square. And again, this was true for every s more than 0.
Yes, ma'am.
Right? So that means the Laplace transform of e to the power at cos kt. Now, what is that going to be? Capital F of s minus a. So that means wherever you have s, you have to replace it by s minus a. And this is going to be true for every s more than a. So that means whenever you have quadratic factors of the form s minus a square plus k square, you can always correlate them with this function, e to the power at cos kt. So that means what? That means we just have to split it into partial fractions and then, solve them and use this result also. So basically, we have to just not just we are not just decomposing them into terms like this. Even if we are able to decompose into terms like this, then also we can write the inverse Laplace, because it is nothing but it's just that we have translated the excess. So that means what? That means when you are translating your s axis, your Laplace transform or the inverse Laplace transform is getting multiplied by e to the power at. So if you are translating by a units, it is becoming e to the power at into your original function, small f. Is this clear? Hmm? Bolo?
Yes, ma'am.
Okay, like for example, just look at your say question number 7 of 7.3. It says, this is question number 7. Okay, we have to apply the translation theorem to find the inverse Laplace transform of fs equal to 1 upon s square plus 4s plus 4. Okay, we have to do this. Now, this is simple in the sense that if you split it, I mean, if you just look at the denominator here, it's a perfect square. है ना? It is 1 upon s plus 2 whole square. Is that okay? Now, to find the inverse Laplace of this means we have to find the inverse Laplace of this. Now, see, had it been inverse Laplace of just 1 upon s square, what would it have been?
T.
Just t, right? But now we have s plus 2 whole square. So if you compare this s plus 2, isn't it something like 1 upon s minus minus 2 whole square? Because I want s minus a. I have a result for s minus a. So I just have to identify my a. So if you compare it, this function with term like this, how much is your a? Minus 2. So if that means this is your ft, small ft, for function of this form, right? So what will be the Laplace inverse of 1 upon s minus a for this kind of a function? It should be e to the power minus atft. So what is a? Minus 2t t. So this will be your inverse Laplace. Is this clear?
Yes, ma'am. Yes, ma'am.
Okay. Now just look at question number 8 then. You have to find the inverse Laplace of, say, s plus 2 upon s square plus 4s plus 5. Okay. Now, just try to split it. Like I have s plus 2, I have s plus 4s here, right? So I can write it as s plus 2 upon s plus 2 square, right? Now, how do I adjust my constant term?
Ma'am, we can write 5 as 4 plus 1.
No, of course. So what if I make a perfect square, so what am I left with then?
Plus 1.
Plus 1. Is that okay? So can I not
Yes.
write it like this? Now I can, sorry, s minus minus 2 upon s minus minus 2 whole square plus 1. Now imagine, now we have to sort of, compare it with s upon s square plus k square, right? Because it's similar and it has been translated to s minus a upon s minus a square plus k square. उसी फॉर्म का हो गया ना? So what is your a? Minus 2. What is your k? 1. For s upon s square plus k square, what is the inverse Laplace?
Cos kt.
Cos kt. And how much is k? 1. So it becomes cos t, right? So that means the inverse Laplace for this function that we are finding has to be with cos t, because इसी तरह का होएगा ना, e to the power at ft. So basically what you have to do is, first of all, identify your small f and then multiply it by eat by identifying your k. यही कर रहे हैं हम, right? So that means it's cos t, but since my a is minus 2, so it will be e to the power minus 2t cos t. Is this clear?
Yes, ma'am.
ठीक है? Now, of course, but sometimes what happens is that we might have to, split into partial fractions first and then use the results. Like, for example, question number 11, if you see of exercise 7.3. Okay, your fs is 1 upon s square minus 4. Okay, now if you see it, it's of the form 1 upon s square minus k square, right? अब इसके लिए तो हमारे पास कुछ है नहीं result, right? ना ही and we cannot even write it as s minus a or something. But one thing I see from here is that I can write it like this, right? Now, this is two linear factors, fine, which we can split into partial fractions like this. A upon s minus 2 plus b upon s plus 2. This is simple, right? Now, that means what we have done is we have decomposed upon our 1 upon s square minus 4 as this. Now, we can always find capital A and capital B, right? Now, quickly, what will be capital A, what will be capital B? Hmm?
Ma'am, 1 by 4 and minus 1 by 4.
So your A is 1 by 4
And B is minus 1 by 4.
and B is minus 1 by 4. यही बोल रहे हो ना? So
Yes,
that
ma'am.
means this is like 1 upon 4 into 1 upon s minus 2 minus 1 upon s plus 2. This is what we are going to get, right? But we have to find the inverse Laplace, mind you. Okay. So that means your inverse Laplace of fs is going to be 1 upon 4 into inverse Laplace of 1 upon s minus 2, है ना? Minus inverse Laplace of 1 upon s plus 2. Now you have to apply your translation theorem, right? Had it been just 1 by s, so what would it have been? Inverse Laplace of 1 by s,
1.
1. So what will be inverse Laplace of 1 upon s minus 2?
E to the power 2t.
E to the power 2t into 1 minus. Similarly, what will be the inverse Laplace of 1 upon s plus 2?
E to the power minus 2t.
E to the power minus 2t. Now, isn't this term similar, familiar? I can write it like this. What is that?
Sine hyperbolic 2.
Sine hyperbolic 2t. But 1 by 2 sine hyperbolic 2t. Is that okay? Hmm?
Yes, ma'am. Ma'am, we can also solve it by using just previous methods at this question. So do we need to do by using this theorem?
नहीं, कैसे 1 upon s minus 2 का inverse Laplace कैसे लिखोगे?
नो मैम, जो मेन हमारा क्वेश्चन था लाइक 1/s² माइनस 4, वो तो
यस
हमारा
मैम,
स्टैंडर्ड
टू
तो।
कर लेंगे, 1/2 से डिवाइड कर लेंगे बाहर तो हो जाएगा।
यस
हाँ,
मैम, सेम
हाँ,
हो
right,
जाएगा।
right, right. But then this becomes straightforward and easier. इसमें कुछ याद रखने की जरूरत नहीं है. But sometimes what happens is, like, if you just look at question number 15 of this, your 15 says your fs now is 1 upon s cube minus 5s square. Okay. Now, of course, you can split it as 1 upon s square into s minus 5. यही करेंगे, है ना? And if we split it into partial fractions, now because of this quadratic factor here, I'll have, that means s is of multiplicity 2. So I'll have a upon s plus b upon s square for s square and c upon s minus 5. यही होगा ना? Now, how do you find the values for such terms? क्या करते हो?
मैम वैसे तो एलसीएम लेकर फिर उसको पूरा स्प्लिट करते फिर फैक्टर्स कोफिशिएंट्स जो है इक्वेट करते हैं लाइक एस स्क्वायर का क्या है एस क्यूब का क्या है.
But at
And
times,
finally,
it becomes
yes,
tedious
ma'am.
and lengthy. Okay. So what we can do here is we can multiply both the sides by s square. Okay. And we get 1 upon s minus 5 is equal to as plus b plus c s square upon s minus 5. Okay. Now I put s equal to 0 here. So what value would you get?
B is equal to minus 1 by 5.
B is equal to minus 1 by 5. Fine. Now, instead of, sort of like we take the LCM and find the coefficients, what we do is if I number this equation as 1, what we do is we differentiate this equation number 1. Why we differentiate? Because it would then reduce the degrees, the powers of s, and we'll be able to find the coefficient simply by putting s equal to 0 there. Okay, so this sort of reduces the efforts in finding the coefficients. Okay, so when you differentiate with respect to s both the sides, your left hand side will be minus 1 upon s minus 5 square, because you are differentiating this equation, and this will be equal to a plus, what will you have, c into something, क्या आएगा? Hmm? Differentiate those terms. What will you get?
मैम एक बार प्रीवियस स्लाइड दिखा दीजिए.
ये लो.
मैम एस स्क्वायर माइनस 10s अपॉन एस माइनस 5 का होल स्क्वायर.
चलो, हाँ चलो बोलो, क्या क्या आया? एस स्क्वायर,
एस स्क्वायर माइनस 10s
हाँ,
अपॉन एस माइनस 5 होल स्क्वायर.
whole square, right? Now again put s equal to 0. So what do you get?
A minus 1 by 25.
A as minus 1 by 25. So that means we have obtained A, we have obtained B. Now what is left? C. Now if I just look at this term again, what did we do? We multiplied it by s square to get rid of s square. Now I have s minus 5. So I can multiply both the sides by s minus 5. Okay. And what do you get? I'm multiplying that by s minus 5. So what am I going to get? 1 upon s square equal to a into s minus 5 by s plus b into s minus 5 by s square plus c. यही आएगा ना?
Yes, ma'am.
Right. Now put s equal to 5.
C is 1 by 25.
C is 1 by 25. Now, isn't it easier?
Yes, ma'am.
Right? So this is another method to ease out the values. You are decomposing into partial fractions. वहां तक ठीक है. But to find the values of the coefficients, there are so many techniques, you know, which will make the problem easier to solve. Okay. Now we have obtained all A, B, and C. So can just any one of you tell me now what will be my Fs now?
Ma'am, minus 1 by 25 s
Minus 1 by 25 S
minus 1 by 5 s square
minus 1 by 5 S square
plus 1 by 25 s minus 5.
plus 1 by 25 S minus 5. Okay. Now, can you find the inverse Laplace now? What I can do is, if I take 1 by 25 common, I'll have 1 upon S minus 5 minus 1 upon S minus 5 upon S square. यही आएगा ना? ठीक है?
Yes, ma'am.
So what will be the inverse Laplace of this? Now I'm not writing everything. I'm inverse Laplace of 1 upon S minus A
E to the power 5t
e to the power 5t minus
minus t
minus t
minus 1 minus 5t
minus 1 minus 5.
5t.
Okay, so this is your inverse Laplace. Is this clear?
Yes, ma'am.
Hmm? Fine.
Yes, ma'am.
So